Hello and welcome back to this live stream. And again, I'm not alone. I'm here with Fabian.
Hello.
And the plan is that today we will calculate some real analysis exercises again. So you see the exercise sheet with the link in the description, and there you can just check out the exercises, and then you see if you're interested in them, and then you can stay here. You can ask questions in the chat. You can ask any questions in the chat. We can do a lot of different stuff as well, depending what you want. But the idea is that we just calculate a little bit and talk and explain some mathematics. So Fabian, you're not at your home, but here at my home. Why is that?
Yes, so you gave the invitation to do a live stream with you in your studio. And I'm very looking forward to it.
Okay, that was my mistake. Yeah, so I have to deal with that, but that's no problem because a live stream together is always fun. So that's what we will see today. So hello in the chat. Please ask the questions. We are exactly here to answer questions today. And calculating the exercise is just that we are occupied doing that. And that we get some material out for questions. So, complex analysis. Yeah, okay, there are some nice questions already. Very good. So, Fabian is here. I'm here. The cat is here in the box. So if the cat moves, don't get distracted because we will still solve the exercises in the meantime. Good. So, good that you are here. I would say we start with something simple because Fabian already prepared the first exercise here. You can download the sheet on the web page. So I said that before, the link is in the title and in the description. So it's really easy to find. So I hope you find it. And then you can also try to solve it for yourself and then check out later here or ask questions you have. Maybe should I scroll through that we see the exercises? So this is problem 1, which is more calculating derivatives. Then I have problem 2 here, which is about even and odd functions. And problem 3 is indeed application of Taylor's theorem. So if you know the video about that, it's exactly similar. Yeah, so we do an approximation with rational numbers for an irrational number. And the approximation should be very good. So this is the claim here. And the last one is, no, I don't say what is the application for the last one. The last one is, some proof. Not a hard one, but some proof. Therefore, this capital show is there. Yeah, so not so complicated. Therefore, if you have some more questions, please ask in the chat. And otherwise, I would say we just start. Maybe I put the chat here on the side. Or maybe just here. Like that.
Yeah.
Okay, very good. I would say, Fabian, you can take the pen and explain what you had in mind for your first exercise there.
Yes. So, hello everyone. This first exercise is around the topic of differentiability and calculating derivatives. So, as you know, there are plenty of rules out there that help us when we want to calculate the derivative of a given function. But sometimes we need to take a step back before we dive into the actual calculation because, well, you always see this variable x here, but we may not be allowed to plug in every possible value of x. So every real number could cause a problem in case, for example, if it renders an expression that is not defined. And this is so as a preparation step and something that you also should consider always when working with a function. Think about the so-called domain of definition of this function. And that is the first step here. And then, of course, we are going to calculate the derivative.
Do you want to answer this question if a computer science degree is a mathematical degree, a mathematics degree? Do you know that?
That's a good question. So I think it depends on where you study computer science and which department computer science is associated with. Some universities just have their own computer science department. But
sometimes it's included in the mathematics department. That's what you mean.
Yeah, sometimes it's together, but I would say they share a lot of similarities. And well, some people just study mathematics and then have computer science as a minor, and other people study computer science and do a lot of mathematics in there, a lot of mathematics courses. And
maybe it depends what you do in your studies, because you can do it very mathematical. Then your computer science degree is similar to a mathematics degree. Did you hit the microphone here?
I touched it.
Yeah, okay, it's allowed. So it depends, but it definitely is very related. And it's more like in the discrete mathematics, I would say. If you do computer science, it's more like doing discrete mathematics. And then it's very similar. So it's definitely related, and then it just depends what you do. Because I would say you can also do mathematics in a very applied sense, and you're very far off from someone that does algebra, for example. So it's like a broad area anyway. But what is definitely true is that you have to learn real analysis in the sense like calculus, like we do it, when you start studying computer science. It's like in the first 2 semesters. So this will help you, definitely. And
yes.
Fabian, you can start.
Yeah. Let's dive in with our first function, f1. I think I have already prepared a copy down here. So the first question that we want to ask is, so if we have this function f1, then it maps, well, its domain of definition, I just call it D, to the real numbers. Yeah, because so the expression here is always a real number, it's a quotient of real numbers. And now we need to ask, well, maybe also give this a subindex 1. So the domain of definition of this first function. So, and something that should always catch our attention when we have an expression that is a fraction, we need to take a look at the denominator, because as you know, we are not allowed to divide by 0. So we need to make sure that every time we plug in something in this expression, it does not give us 0 as a result. So we do not divide by 0 here. So one could think, okay, maybe one problem would be if we plug in x equals 0. So then this first summoned here in the denominator would be 0, but e to the 0 is 1 again, so this won't happen. So in fact, so what we can see here is that no matter what we plug in, so x squared, as it is a square, will always be greater or equal than 0. And e to the x, and then also the square, will always be strictly greater than 0. Yeah, so this is one property of the exponential function that we use here. So even if we plug in a negative number, for example, for x, well, we will get a strictly positive result here. So, and the sum of a number that is greater or equal than 0 and one that is strictly greater than 0 will always be strictly greater than 0. And in particular, it will never be 0. So we don't have a problem with the denominator in this case. And this tells us that in the case of the function f1, the domain of definition d1 is actually all the real numbers that we have here. So we have done our first check. We now know that f1 is a function that goes from R to R.
Quick question there. This is your choice for the domain of definition?
Yeah.
Because you could also choose a smaller one?
Yes.
Depends what you want for the function. So the exercise is a little bit strange. Because usually you would say, I have a function and the function needs a domain. Otherwise, it's not a function. It's like you need a set on the left and a set on the right. So a domain and a codomain. So the exercise is more like, think how you could define the function in the best way. Whatever best means in the situation. But here it's very clear. You just want a subset of the real numbers and how large can you choose it. And that's exactly what you answered. Yeah? Check if there are some problems with dividing by 0 or something. But here you don't have that. So it's very good. So you have exactly a function from R into R.
Yeah. So
yeah. There's a question. Could it also be subset R? Yes. You could say I exclude 0 for some reason. I just take the interval from 0 to 1. Depends on the problem you have. If your function models something and where there are some bounds in the domain naturally given, that the function only makes sense for x values between 0 and 1, you would choose the domain 0 to 1 and not more. So actually it depends what you want, but therefore the question here is, can you enlarge it in some sense that you have all the possible x values in? And the answer here is, yeah, you can choose the whole set R and not a smaller subset. But you can choose a smaller subset and you still would have a well-defined function. But you would not have solved the exercises like Fabian wanted it. So that's the thing. Yeah? The exercise is meant in this way.
Yeah.
That's what you have to know if such an exercise occurs to you.
All right.
Yeah, that was not the main part of the exercise.
No, this is but yeah, this is always something that you should think about, is the validity of the expressions that you want to turn into a function.
Indeed.
Yeah. And now we want to calculate the derivative, and the rule that that pops into my mind when I see a quotient like this is the quotient rule. So let's recap that maybe quickly, because we need some preparation then to calculate it. So let's say f1 of x can be written as a number or as a function u of x for the numerator, and divided by, let's maybe use another color here.
You have enough colors.
Yeah, I have a lot of colors here. So let's say v of x for the denominator. Then the quotient rule tells us the following. I'll write this a little bit nicer. So the quotient rule allows us to transfer the differentiability of the numerator and the denominator to the differentiability of the whole fraction. Yeah, so we need to know something about u and we need to know something about v. The other thing we need to know about v is that v does not attain the value 0 here, which is something that we already checked here. So the quotient rule now tells us, if we want to calculate f prime of x, so the first derivative, what we do is we first calculate the derivative of u prime of x, and we multiply it with v. And in the next step, we subtract u of x and multiply it with the derivative v prime of x. And in the end, we divide everything by v of x squared. All right. So this is the general rule. And what we need to do here in the next step is we calculate now the derivative of u. So what would that be? So u in our case, so maybe also still have some space here. Let's write down u and v as well separately. So u of x is the numerator, so it's x squared minus e to the x squared. And v is the denominator. V of x is x squared plus e to the x squared. All right. So now let's calculate the derivative. So this boils down now to a simpler rule. So for the first summand here, x squared, we know the derivative is just 2x. This is calculating the derivative of a polynomial. And for the second part, here we need to apply another rule, namely the chain rule. Yeah, so we keep the minus here, and the chain rule tells us, so we first take the outer derivative of the exponential function. So the derivative of the exponential function is just the exponential function itself again. So this part stays the same. And then we multiply everything by the inner derivative. The inner derivative, or the inner function, is x squared. So just like here, so the derivative of x squared is 2x, so we multiply everything by 2x. So I write down here in the parentheses also the rule that we use, the chain rule.
So you use every rule you know for derivatives in your exercise here?
Apparently, yeah.
Yeah, very good.
So we also use the rule that if you have a sum or a difference of functions, the derivative of the sum is just the sum of the derivatives. Yeah, so we boil it down into smaller and smaller packages, which we then can differentiate individually, and then we plug in, or we put everything together in the end. So now let's do v prime of x. So here we start again with x squared. So this stays 2x. So, and for this term, so we now have, so this is now as a different function than the one that we had before. So now the outer function is the function that takes something to the power of 2. So the outer derivative would be 2 times, well, whatever is inside, e to the x. Now the inner function that we have here is e to the x, which is, if we differentiate it, e to the x again. Yeah. So, and we can also simplify that and write it together as 2x plus 2 times e to the 2x. Yeah, by using also rules that we know for powers. Okay. So now if we go back again to our quotient rule, we see that we now have calculated or written down all the ingredients that we need. So last step is now to write down the first derivative of x completely. So for this, well, it's now just copying and pasting. So we take the first derivative of u, which is 2x minus e to the x squared times 2x. So this is our u prime. And for v, we just multiply the expression that we have here.
That's crazy. It's so big.
Yeah, so that's what happens if you want to.
Yeah, it's good that you do
well,
that.
if you want to do some expressions that are a bit complicated, yeah, it gets it can get messy. Therefore, it's always good to write down the individual terms so you have some steps to go back to. And if you make a mistake, it's easier to track the mistake. And hopefully you are tracking every step that I do and can tell me if something goes wrong along the way. So I'm now writing down u of x, and I need to multiply it with v prime, which is 2x plus 2e to the 2x. All right, and that's just for the numerator. Now comes the denominator. So I think it was a different method to draw this line.
Okay.
Yeah, because the expression is too large, so I need to beautify it a little bit, at least.
Will you simplify it in the end again? Or will it stay very big? Because that's how the derivative looks in this example.
Yeah, so I think that's how it looks. So there are some terms that we can use to simplify it.
Okay.
We can have a look and discuss it. but I think for the purpose of this exercise, which is not about simplifying terms but calculating derivatives, it will be fine.
Okay.
If we just leave it like that. So e to the x squared. So, and this, we need to square it again. Yeah.
So
that's it.
That's very nice. There are some questions in the chat about continuity, but maybe we can go a step further. How do we know that this function is differentiable, which includes continuity then? So maybe that was also stated in the problem, and maybe you talked about it a little bit, but it's a question again. So maybe you can elaborate a little bit.
Of course. Are we still online?
Yeah. Everything works. No problem.
Yes, so it's a good question to ask about continuity. And continuity and differentiability are related in the term that if we are on an open interval, differentiability is actually the stronger property. So if a function is differentiable, it is in particular continuous. So, and how do we know that this function f1 is differentiable? So you could say, well, I just calculated the derivative, so that's it. Yeah, but there's a bit more to it, and this is why we...
It's not the other way around. Like, you can calculate the derivative because it's differentiable.
Yes.
But you're on the right explanation, of course.
Yeah. So it's the other way around. Yeah. So actually, we need some rules beforehand that tell us this function that you see here is differentiable, and that's how the derivative looks like. And this is how all the rules that we apply here implicitly sometimes, because we get used to it. We see an expression, we take the derivative. These rules work in exactly that way. Given that the function, for example, is a quotient of differentiable functions, then the function itself is also differentiable, and the derivative can be calculated just as we did it here in this example.
Yeah, quotient rule. Yeah. That's stated in the quotient rule. The quotient rule tells you how to calculate, but it also states beforehand, the quotient of two differentiable functions is differentiable again. Yeah. So it's two parts. First, this works, and this is the formula, how it works.
So you can also think about the following question that is much easier than the one that I solved here. The question would just be, is the following function differentiable? You could just say yes.
Which one?
Yeah, is f1, for example, differentiable?
Yes.
Yeah, you would say, well, it's differentiable because of the quotient rule. It is made up of differentiable functions u and v. Yeah. So you translate the problem maybe to another one, which is, well, why do we know that u and v are differentiable?
And why do we know that u is differentiable?
Yeah, because u is a sum of differentiable functions. Okay, so we have a summoned one and a summoned and a second summoned. The question then would be again, so why is each of the summons differentiable? And this is where you really boil down the question of differentiability to, well, a core that is easily answered.
Maybe let's answer that. Why is x squared differentiable as a function on R?
Yes.
Everything is defined on R.
Yeah.
Why is x squared differentiable?
So there are two ways, I think, to answer this question, depending on what you know already. So I think the easier way would be to say, well, it's a polynomial, and we know.
No, that's indeed the answer I want to give here.
Okay.
Because that's something you learn immediately after introducing derivatives and differentiability, that all polynomials are differentiable. So you don't have to boil it down even more. Just remember that fact. Polynomials are differentiable. By definition of the differentiability. Yeah, that's really simple. It comes out. And we also get the rule how to differentiate polynomials.
I think actually you can even make it simpler. You say that monomials are differentiable, and then you just get all the differentiability of the polynomials by adding. Indeed. And for the monomials, we have this easy rule. If you have x to the n, and you take the derivative, it becomes nx to the n minus 1 and for n we just take the natural numbers.
Yeah, this is a funny rule because usually you learn this rule often before you even learn what differentiability means or how it is really defined. So this is interesting because it comes out of the definition of this prime, of the derivative, but often you learn that before you even know what to do. So therefore this rule is so into this, so useful, or so important, but also so easy. Yeah, so you need to remember it.
So it's something that you just don't think about anymore if you take derivatives. But you rediscover it again once you separate complex expressions into its atoms, so to speak.
Yes, there was a question in chat with the absolute value or polynomial divided by absolute value. We know that the absolute value is not differentiable at 0. At all other points, it's differentiable. So this question boils down that you don't have a problem outside of 0. But at 0, you have to check what happens there. And then there's no general answer first. You have to check what happens at this point.
Yeah, it depends on how your polynomial is built in the end. As the easiest case, you just take a constant 0 polynomial in the expression that you saw there, then differentiability is easier. But if you take another one, then, for example, if you just take the polynomial that is linear, just x.
Then it does not work. But we don't go into details there because it's just a lot of explanation now without writing. We had the question with A2, I guess you called it. So why is the exponential function differentiable?
Well, actually, it's not the exponential function, but it's a concatenation of. So because the function that we see here, A2, is a composite or concatenation of two functions that are differentiable.
A composition of two differentiable functions.
Correct.
And the result is it's differentiable again.
So by the chain rule.
With the chain rule, yes. The chain rule again has two parts. First part, composition is differentiable again if you put in two differentiable functions. And to calculate the derivative, you get the formula in the chain rule.
So, and maybe just for being very, very complete here. So the exponential function is differentiable. This is something that we also learned and checked somewhere in a course. So this you can take for granted. And then x to the square.
It's not so hard to show. So that's also a standard exercise. But at that point, you know, this is a differentiable function.
Yes. So, and then we have also talked about now the differentiability of A2. And now, well, if you trace back our steps, you will see, okay, so A1, A2 are differentiable. So is their sum or their difference because of the sum rule for differentiability. And, well, now we do just the same steps for V. And then we have really step-by-step explained why the quotient rule is applicable. And then we plug in the expressions that we can calculate it to get this
very good.
Not very handy expression here.
So that was all. So you break it down to the smaller parts and then you argue with the rules we have. I think that's all the exercise wants, and then it also wants that you apply the formulas, which Fabian did. And the result is not pretty, but that happens a lot. If you deal with complicated functions, the derivative can explode in the size.
So therefore, it's really important that you try to write down the steps that you take, and so you can easier check whether you made a mistake or not.
Okay. Do we have questions for exactly this kind of stuff we do here? So calculating derivatives with chain rule, quotient rule. Sum rule was included. The only thing missing was product rule, but you could say quotient rule, product rule are related. So I think we have everything in. So differentiate again. So second derivatives. It's not so complicated because the idea is the same. You still have a quotient. It gets larger from the size you have to write, but from the ideas it's not more complicated because there's no new derivative in the parts you have to calculate. Yeah, so this exponential and then the inner derivative comes out. Exactly the things happen again, just more times. So you don't need more ideas. So therefore, I don't think we need to do that. But I see it was a joke. So yeah, of course it was a joke. We will not do that. I already thought this is a joke by Fabian that he really wants to calculate this, but he did. So very good. So any questions? I don't see any related. So now there's a question from me. Fabian, do you want to calculate the next one, or should we jump to the first to another exercise and then you come back calculating? I don't know which one you want. Otherwise, the people in the chat can say if they want another one of the problem 1. Otherwise, we could switch places and I calculate problem 3, or I explain how to do problem 3.
Yeah, then, why not do that?
Yeah, then you have a short break.
Okay.
It's also not a short exercise, so it will take some time.
All right.
Otherwise, just put your questions in the chat. And then I don't see a problem with going back. So let's see, I can copy that maybe to some place here. Oh, where's it? So
should we switch places, or should I just stand awkwardly behind you?
No. Sorry, Fabian. Yeah,
it's just better if I stay here.
Yeah, you can take care of the cat. And yeah. Problem 3 is like application of Taylor's theorem. If you don't see that yet, then maybe the question is not in the correct background, because usually such a question occurs if you introduce Taylor's theorem. I think you also thought of other ways to do it, and that's definitely possible. But my idea would be to use Taylor's theorem, which means approximate this square root with a polynomial, a Taylor polynomial. That's the whole idea here. So what can I do? Maybe I write it down what I want to do. And this one should be a rational number. And this one is our irrational number. Maybe I should write it to it. Irrational number. So this one is definitely, maybe you already see that, Fabian. It's between two numbers we can already say. So it's between 1
and 2.
Because the square root of something bigger than 1. Yeah, and it's the square root of something smaller than 4.
Yeah.
So it's between 1 and 2, that's already for sure. Now the question is, can we approximate it better? And here's how we should approximate it better, so that these two digits are also fixed in some sense. We will see that. There's a question again. Can we conclude that f is a differentiable at the limit? Which f? So maybe there are some backgrounds missing, I don't know, for the question, but we can answer that soon. Maybe I first do this exercise here. Okay, so the idea would be to use the Taylor polynomial, and maybe let's check this. So if you know the Taylor polynomial, you know what to do. Polynomial, so. Then you know you need a function first. So what could be the function we need here? F of x. So because we want this square root, what we need is a function that has a square root in it. So that's not so surprising. And we already know the square root of 1, so we could say, okay, we can write a function as 1 plus x. Would be one example, because then we would expand the function around 0. So maybe we sketched it first. I think a sketch would be helpful here. So at 0, what happens at 0, Fabian? The function is 1.
It's 1. Yeah.
So the square root is a little bit shifted. So the square root function, you usually know it looks like that. Yeah, roughly. So now let's say our there's 1, so let's say our 1/2 is here. So we want this value, the y value. So f of 1/2 we would like, because that's exactly our square root of 3/2. Hello and welcome. Always new people, so welcome to this live stream. We just calculate some problems. If you have questions, just put them into the chat. So now, you know the Taylor polynomial, and the first one, the linear approximation, would be, if we expand it around 0 here, which makes sense, because then we just put in 0, and then every square root we have is just the square root of 1. Which is important, because we can't calculate the square root, we just want to have rational numbers in the end. So now, let's say this is the linear approximation. And you know, Taylor polynomial also gets you a quadratic approximation and so on. So now this linear approximation you already see, maybe that's already a very good approximation for the actual value we want. That's a little bit off, but gives you an approximation. So that's the idea here. We approximate with a Taylor polynomial, and now let's see how much we have to do. Taylor polynomial, Fabian, means we need derivatives again.
Lots of derivatives, depending on the order.
Indeed. I will calculate them, but Fabian already showed he's very good at calculating, so please check if I do it correctly. So we have the square root, which means factor 1/2 comes in front, and the inner derivative is not really there because just factor 1 from 1 plus x. So this is really good. This was my first mistake, so I want to write it as minus 1/2. So we reduce the exponent by 1. So a generalization of the rule Fabian showed before. That's why this rule is so important, because it also is applicable to fractions in the exponent. In particular, this one, I always have to write it down, because I always forget that some people forget about that the square root is nothing more than the power 1/2. So this is, if you know that, it's not a surprise, but sometimes you forget about it, that this is just the same thing. It's just writing the square root with an exponent. And then reducing that by 1 means we go to minus 1/2.
It's a good idea to rewrite square roots with exponent the way you did, because it makes calculations easier. Then you don't make any mistakes, because it's much more mechanical to reduce the exponent by 1 than to
you are absolutely right.
To change a square root by some other type.
In the moment we have to subtract minus 1 here, which we do with derivatives. We should definitely write it as 1/2, because otherwise you get crazy. How to write a square root, and then always do that. So good tip, good hint for that. Next one, second derivative. 1/2 stays there, and then we get minus 1/2 in front. I put the minus 1 separately, because easier to write. And then we have 1 plus x to the power minus 3/2. It's reduced by 1. So you have to subtract 1. So 2 halves. Okay, very nice. Can we do more? Third derivative. So now 1/2 comes in front. Stays. Everything stays. And then we have times 3/2. Actually minus 3/2. But I want to put that into the same sign. So we have minus 1 to the power 2. And here we have 1 plus x to the power minus 5 divided by 2. So it gets bigger in the negative sense. So
maybe we need to move the writing a little bit to the left.
Yeah, thank you. This is, I didn't see that.
Yeah, or we do it like that.
No, you're right. It's much better to just use our face. Sorry, I didn't see that the camera was on top. So now this is the result. And we always reduce by 1. That means we go steps by 2 in the 1/2. To see the pattern, yes, it's an easier way. That's why I already did it like that, to write it in the sense that you see the general rule, and then you could prove it by induction. We will not do that because we don't need all the derivatives. We just want one approximation. So we will stop at the 4th indeed. But you already see the general rule then, I hope. So what we can do is to say, and Fabian, you are with me to see if I do it correctly.
Yes.
We have 2 to the power 4 in the denominator. We have And now you see that we have 1 times 3 times 5 in the numerator. And maybe that's good enough for the first part. So this one is the same as before. And we have minus 1 to the power, yeah. Should I do it like 4 minus 1? Yeah, maybe I write 4 minus 1 that you already see. It's just 1 less than the derivative. And this one is 1 plus x to the power minus 7 over 2. So now you could formulate a general rule, like the comment in the chat. We have 1 times 3 times 5 times 7 in the next one. Here is 5 minus 1, and here is 9. And there's 2 to the power 5, so we can do it. You can do this general formula, and then you prove it by induction. That's maybe a good exercise. General formulation, possible. Okay. We need to justify that in what? Why is there a heart over this? Analytical function. So we don't need that. What we need is an approximation for the point at 1/2. Of course, it would be nice if we can make this approximation better and better, and in the end that it approximates it in the limit exactly. But because we don't state that in the exercises, in the exercise here, we don't need that. We just have to check if the Taylor polynomial as we define it to some order approximates it. Which means if it goes away again in the limit, we don't care because we still have an approximation. So you are right, it would be nice if we have this analytical property, but we don't need that for solving the exercise. And you're right, of course, we also have that for the function, but we don't care at the moment because we just want an approximation. So Taylor polynomial approach is a good one. If it works, well, we will justify that with the result. That's what I'm doing here. Okay, I hope this was clear. Did you understand what I what I tried to explain? Like it's like a trial and error first, and if it works, it's good. Okay. Taylor polynomial. Let's calculate one, and let's say we do the one of third order. I don't want to write it, so I do that. So Taylor polynomial, let's call it T3. T3 of x or h. I'm never sure what I use in the videos. Maybe you used h. Let's use h, just to spice it up a little bit here. Of course, the name of the variable does not matter. So what is the Taylor polynomial? Horrible to write fractions and exponents with text on a line. Is it horrible?
I think it's readable, so I haven't noticed.
It's if you write it on paper. Yeah, you can mess up some stuff if you don't distinguish the exponents and fractions. I think that's what he meant for writing for yourself. Yeah, you have to be careful to keep the line and to see what are the exponents and what are the fractions in the exponent. Yeah, okay. So there you have to learn how to do your writing, that you see that. Okay, what do we have here? Taylor polynomial. The first one is f at 0 plus 1 divided by 1 factorial f prime at 0 times h to the power 1 plus 1 divided by 2 factorial f second derivative at 0 times h to the power 2, and then the same with the power 3.
Yeah, so maybe we can quickly explain what h means, or how we can, maybe we can even visualize it in the plot above. We need also to make sure that the polynomial is not
our
hidden
faces.
by our faces.
And maybe I just copied the nice plot here.
Yeah, I think that's easier.
Did you say our nice faces? Yes, we need the faces because we want to gesture some things, but otherwise, yeah. Maybe the mathematical explanations are good enough. Yeah, LaTeX code on paper, but it's hard to write every calculation you need to do that directly in LaTeX. Then you also make LaTeX mistakes, I guess. Yeah. That's what that happens to me at least. Okay, you want to explain that, Fabian? What H means here?
Yes, sir. So the idea is, so we have these two, or the first ingredient to the Taylor series, or the Taylor polynomial, is the base point that we use in order to write down this polynomial. And I think we use the point x equals to
0.
To 0.
Yeah, that was the Taylor polynomial around 0.
Yeah, and so we see this 0 here as well in the polynomial as we wrote it down, because this is the value for x that we plug into each derivative of the function f. Yeah, it's f of 0, f prime of 0, f double prime. So, and the next thing that we do is that we multiply this with, well, that what makes the polynomial. So this monomial factor that we carry, which is always, it's always the distance to this base point that we use, and we call this distance h. So maybe this is also notation that comes from this difference quotients that one uses to calculate derivatives. So h always means this length or this distance here. Yeah. And in the end, so we already have, I think, also a candidate in mind, what we want to plug in for h, right? So I think we want to plug in 1/2,
yes,
right?
But, yeah. So we already know that we want to go to 1/2.
Yeah, but h can
is a variable.
Can be any number.
Yeah, so any number, and because we want to plug in 1/2, we could say h is between 0 and 1/2, because we don't need to go further than 1/2.
Yeah.
And that's all. So and then we plug in 1/2 in the end, because that's what we want. We want the approximation at this point. So here was the linear Taylor polynomial. We want to get this value. This value here. For the Taylor polynomial of degree 3 now. So we have some cubic function, but it looks similar. Like here, we have one point that is close to the actual value we want. Okay, so h goes to 1/2 in the end. But at the moment, it's just a variable. But we can already put it in if we want. So because that's the Taylor polynomial we want. Yeah, maybe we do that. Fabian, good point. Let's immediately calculate the value we actually want. Maybe now it's a little bit tricky. We want all the derivatives on paper. Yeah, okay, let's just scroll up again when we need it. So now above our face, maybe here. So T3 at the point, or at h is equal to 1/2. So let's do it together. First is f of 0. F is that function here. So we just have 1. Square root of 1. Yeah, that's important. And yeah, the question if the linear function is suffices, I would say no. But we will see that this one is good enough. But you just can try it out. So now let's see. We have 1 plus, yeah, there's 1 again. And now we have the derivative at the point 0. Maybe we go up again. Here, derivative at 0 is the one that we are interested in. So, and we see it's just 1/2. Yeah, we just put in 0. Well, very good. Very simple. So now we don't forget about that. It's 1/2. So we have 1/2, nothing else. And we put in h is equal to 1/2. So we also have 1/2. Maybe I make it green. Then you see this was our h. Okay, then the next one. We have 1 divided by 2 factorial, which is this 1/2. Then we need the second derivative at the point 0. So what do? We put in 0 into the second derivative. And this one is here 0. We put in 0 here, which means this whole square root with the power 3 everything which is complicated in general vanishes with 1, and we just have minus 1 over 4. So this is what we put in. Maybe we also write it as minus 1 over 2 to the power 2, to just have 2's involved and not the 4. And that was that. And now we put in h again. Now h is 1/2, and now it's squared. Yeah, very nice. I like that. So we have a lot of 1/2s involved. Okay, last one, third derivative. So we have 3 times 2 times 1 for the factorial. I write it like that immediately because we want the 1/2s. Times, and now comes the third derivative. Oh, we are again over. Maybe I have an idea. We can just put the camera to another place. What do you think? Just for the moment.
I think that makes it easier.
Just for the moment. We change it again. So now let's see. I scroll here to the third derivative. And we put in 0. Okay, a lot of halves again. What do we have? We have 2 to the power 3 here in the denominator. We have times 3 in the numerator. This is just plus 1, and this one gets 0 again. So maybe again, this whole ugly thing, we put in 0 and it vanishes to 1. So this is what we want. So this is the thing we have. So let's go down again and let's put that in. I forgot it again. It was 3 divided by 2 to the power 3. Ah, yeah.
Have it up there.
Okay, and this one now with h to the power 3. So we have 1/2 and now power 3 again. So you see we have a lot of 1/2s. And now the idea is to put that in. The teacher uses all my courses. Yeah, very good. That's why I made the videos, that they can be used. So now, we have to calculate it. We want a rational number in the end, because that was our question from the beginning. Can you find a rational number? And that's our rational number we want to find. Okay, this will be a little bit of work. Let's see. This one is 1 divided by 2 to the power 2. Not so complicated. The next one is minus. And how many 2's do we have in the denominator? I count 2. Let's see. I count 1, 2, and 2. So 5. Yep. So 2 to the power 5 plus. So now the next one. I already wrote it like that. This 3 can vanish. Very good. We only have 2's. That fits together, but it's not really needed. We could also work with a 3, but with the 2's is much nicer now. This is 3, 3, so this is 7. 2 to the power 7. Okay, now calculating with fractions means bring it to the 1 denominator. The 1 denominator would be 2 to the power 7, which means we have the 1 as 2 to the power 7 plus the 1 with 2 to the power 5 minus 2 to the power 2 plus 1. Okay? I ask you, Fabian, because you are the first one that can find mistakes here.
You are trying to write down everything with the common denominator. Yes. So the 1 becomes a 2 to the 7. Then it's always the difference. Yeah, for 2 to the 5.
Yes, this one.
2 to the 2. 2 to the 2.
Yeah, so we multiply this with 2 to the 2.
Yeah, and the last one just is the one that you already have.
It's just 1.
Yeah.
Or
2 to the 7. Yeah.
Okay, very good. So now we need the numbers. So what is 2 to the power 7? I need a line here. So maybe we can write it down. 2 to the power 7.
32? No?
No, sure. No, 128, I would say. And then we also have that here.
Yeah.
And 32 would be 2 to the power 5.
Ah, yes.
Makes sense, because we have 8, 16, 32, 64. So you can go through all the bytes.
Yeah.
So this is really common numbers, but yeah, you just put it into the calculator if you're not sure how many 2's you multiply, and then you remember that. -4 + 1. Okay, oh yes, that's it. I think we just put it together. What is it? It's 160 here. -4 + 1. So 157 divided by 128. It's between 1 and 2, like we wanted it from the beginning. And now it's the question, should we write it in decimals? Yeah, maybe. Can we do that? So I just, yeah, a calculator would help. Let's do that. So it's definitely 1 point, now I don't remember so well, but I have a calculator in my pocket and we just calculate that. Or should we calculate it together? No, you can just put that into any calculator. This is really not complicated. And it's a rational number, so the decimal numbers will stop at some point. So we can write down all of them. Yeah, this is just to get a feeling. Of course, the rational number is the same as the left. So this one would also be your solution for the exercise. But this is good because we would think of the square root as an infinite decimal number. Yeah, so that would be the finite approximation in this time. Using Euclidean algorithm. Yeah, you can do that. That's what I don't want to do now because it's not part of the exercise. And it just goes into a complete different direction. So maybe Fabian wants to do that, but we will not do it. We just use the calculator now. Okay.
So I'm fine with the calculation. The question is whether we have now solved the problem with this number, because it's clearly a rational one.
Okay, before you say that, maybe I go back to the exercise, because I formulated the exercise exactly like that you are closer to the irrational number with that number here. So, and that was by choice, because if you have this accuracy, this how accurate you are, so how good your approximation is, then we know something about the digits we see now. Let's see here. So I want that. I want that this, what should we say? This one is equal to, oh no. How should I write? Yeah, maybe equal, doesn't matter. Maybe approximated. Not so important. So plus minus this accuracy. So this one tells you if you are off by 0.003, it means the first two digits after the decimal point will not change. In other words, if you have this as your approximation, how should we say it? Our estimate. So how good your approximation is. If we have that as the bound, as the exercise is stated, then it means we definitely know the first three digits here. 1, 2, 2 are safe. Because if you add here 3 in that digit or subtract, you will not change the first two digits. And that's important to know. These are the safe digits in the case. So, but now Fabian can tell us if we actually know that. Oh, maybe question mark first.
Yeah. So for this, I think we need to once again remind ourselves how a Taylor polynomial works. So the first thing that we always specify, or that we already specified, is what is our base point, then what is our h, so the distance to the base point, and then the third thing that we need to fix is the order. And the order specifies how many of these monomials do we add. And so now if you think about sums and how sums become series, well, of course, we can also stop our series at a later point, and the only difference between, well, the Taylor polynomial of order 3 and the Taylor polynomial of order 4 will be this last summand that we add, or this last term. And well, this is what can change the result here. And yeah, what we need to do now is to estimate, well, this difference. And there's also a nice formula for that. So we can actually estimate the difference on everything that we can attain here by this formula. How is it called again?
It's a remainder formula.
For the residual.
Yeah, or a remainder term.
Yeah.
I would say a remainder term to keep it clear. And I wrote it in exactly that sense. Now this one, we want to keep below this threshold from before. Yeah, 0, 0, 0, 3. This is the threshold we want. This distance should be smaller than that, because then we have to save 2 digits, or 3 digits if you include 1, but after the decimal point. Because the one we already knew with the first statement is between 1 and 2. Yeah, so the one we already knew, this is new information. Yeah, this was something we didn't know if we don't have a calculator by hand. And you don't need the calculator for calculating this one, because you know the Euclidean algorithm. So this is Taylor's theorem. Indeed, how good is the approximation? And the approximation is now the remainder term. So this one, I rewrote that, because now you see this is the difference between the function, the original function, and the Taylor polynomial of degree 3. And now Taylor's theorem says, okay, this is a remainder term. This is not really hard, because it's just, yeah, maybe you also call it 3. Depends. Sometimes it's called 4, but let's keep it at 3 at the point 1/2. So the remainder term is just the difference by definition. So not so complicated. But Taylor's theorem tells us that we can estimate this remainder term, or that the remainder term is given with an intermediate value, if you remember that. So maybe we write it down as a formula. The remainder term, so now we want to estimate, and if this estimate is good enough, then we say, okay, this estimate is lower than the threshold we want, and then we have what we want. Yeah,
yeah. So for x, we also plug in
this is what we want.
The 1/2, right?
For x, what is x? Here, yes, sorry, very good. That was the point we put into the function, because this is actually our square root. Yeah, maybe I should mark it again. I just changed the order here. Yeah, this is our square root. So now we have a general statement, we have the general remainder term, and now I just write it down. So let's say the remainder term for the third order is given, and now it's the funny thing of Taylor's theorem, is given with the fourth derivative at a point which is intermediate. The fourth derivative I write with this superscript. And now intermediate point, yeah, okay, different names. Let's say we choose the Greek C, because that's usually used in that case. Times, and now comes x to the power 4 again, and x is 1/2 here, so, or h. To be concrete, we chose the name h. So this is our h again. Power 4. So now this c, we don't know. So that's the disadvantage. Yeah, we don't know, but this helps us still for an estimation. We know it lies between the expansion point and the value we put in. So we know exactly it lies between 0 and 1/2 now, which is good enough as an information, because we just could look at the worst case in that situation for C. And that's what we need here for getting this estimate. So for getting the inequality, we just need to put in the worst case, and then we have it. So now that's what we do. Let's say I write it as absolute value of 0.1/2. 1/2 is actually our h. So maybe I should put in a green fraction again, just to keep it clear. Okay, now fourth derivative, Fabian. Yeah, this was, I write the factorial like that. And now let's see, what was the fourth derivative? Maybe we copy that to the bottom.
Yeah, good idea.
Because, I don't know, I can copy it completely, because we actually use the whole thing. Yeah, so let's delete that. We just, instead of x, we have xc. Well, this was really not so easy. Xc. So now the absolute value. Don't forget the absolute value, which means, first of all, this minus sign does not matter at all. Just let's delete it immediately. it just vanishes in the absolute value, and the other ones are positive, so we put them in front, and now the absolute value we just use for this square root to some power with the xi involved. So now let's start with that. What can we say about the square root here? So first of all, maybe we can put the minus sign away and say this is in the denominator. If we do that, then it looks much nicer already, because it tells us we divide by something which is bigger than 1. Because we put something in that is bigger than 1 or 0. So this worst case I described before would be the case that xi is equal to 0, because then we divide by the smallest possible number. So the output is the biggest value we get. Should I say worst case? I guess. In the worst case, xi would be 0, and then we would divide by 1. So the whole thing can be estimated by 1. Odd and even numbers are only defined. Okay, this is a question about odd and even numbers. That's something we can answer later, because not related to the exercise first. Okay, so now this one we estimate by our 1, which is nice, because now this is gone already. Okay, gone in the estimate, yeah, so we don't have to care about that. What can we do with the numbers here? I would say let's cancel the 3 already, and let's put the 2's together. And how many 2's do we have? Oh, I forgot this one.
Yeah.
We also have that from before. I put it next in the correct order as before.
Yeah.
Okay, but now all the 2's we have, we can put together already. So let's say here we have 5 divided by, oh, what do we have there? We have 2 to the power 2 times 2.
Yes.
This was the 4. And then we have 1 divided by 2 to the 4, which was before. And we have there that again. Okay, so as before, we have a lot of 2's. Or powers of 2's. Which you know how to calculate. And okay. So let's do the thing. We have here 2. The cat awoke?
Yes, sir. Sure.
Okay, so what we have here is 5 times, and now 1 divided by a power of 2. What could that be? We have 2, 8, 10, 11. 2 to the power 11. Okay, now comes our estimate. So what is 2 to the power 11? Okay, cat wants to go. And we have 5 divided, and now we have a big number, because we have 2 to the power 11. Okay, I help the cat go down. So this is 2000. What do we have? 2048. Yeah, 2 to the power 11, because 2 to the power 10 would be 1024. So I guess that's a correct calculation. I can estimate that by dividing less, which is 2000. So it's definitely bigger. And now, okay, I put that into a decimal number again. What is it? 0025? Is that correct? It's like times 4. No, times 5. Maybe I should use the calculator to be sure. But you can check that as well. So then we have 0025 here, which is actually less than the number we want. 0003. So there we have it. This is our estimate. And now we can summarize. Our approximation, our Taylor polynomial, gives us an approximation, and this is good enough for what we wanted. Because it's less than this number. And the 2 digits from before, here, these are the safe digits. So we actually know now that our, maybe write it down, the square root 3 over 2 lies between two values at least. So what can we say? This is 1.22. What was our upper bound now? 6, 5. So now we can say it's 9. Yeah, I say 9, 5 something. And on the lower bound, we just subtract 3. So we have 1, 2, 3. So yeah, and then was also 5.
Yes.
Point. Okay, so we know even more than before, but this is what the Taylor polynomial gives us. A rational approximation of this irrational number. So any questions for that? I think it's a good exercise for checking that Taylor's polynomial is actually useful for calculating with numbers. Yeah, and for approximating some irrational numbers. So I don't see any questions for that. So therefore, now we can decide what we do next. You're up to something, Fabian? Because now it's your turn again.
Yeah. We can do another exercise.
So you can choose one of your exercises, but please still put questions for these exercises into the chat, then we can answer that. Otherwise, Fabian, what do you want? We have a lot.
Let's maybe do one that does not do so many calculations. It's a little bit shorter, so we can do the second problem that I brought.
Yes, that's a very good one. So maybe I copy that for you, and then we change places again.
Cool.
And I hope this explanation was good enough for you that you could understand how we use Taylor's polynomial. If not, there's still a video. Oh, I didn't copy everything. There is still a video about a similar exercise where I do this a similar thing with the logarithm. So we have a logarithm at some point and we want to approximate that. So now again, this is the exercise. We scroll down and then we continue. Yeah, this is... why is that not working, Fabian? Okay, I'll try it again. One last time.
Maybe look at the text.
This is a long text. Maybe that's the problem. Okay. Okay. Sorry for the delay, but with this delay, you can think about the exercise already. And yeah, maybe that's good enough. Fabian, you can explain. Pi would be nice to approximate. Yeah, pi could be approximated in a similar way if you find the correct function and the correct Taylor polynomial. So also a good idea. And okay, so
we switch again. All right. So this is sort of a proof function, a proof problem that needs a proof. So we don't have a particular function given that we need to differentiate, and so there are, well, two sub problems here, but they are very similar. So given that we have an even function and that is also differentiable, we want to show that once we take the derivative, the symmetry property changes from even to odd. And similarly, given an odd function that is differentiable, we want to show that the derivative is even. So if you recall this little rule or that we had on monomials, you see that this is actually what happens there. So we change from, let's say, from x to the 3, which is odd, we come to x squared with a prefactor. X squared is even. So we see that it works for monomials, but it even works in a more general context.
Can you write down the definition for even? Because maybe it's not completely clear.
That's a very good remark.
And also for odd, so that we have both definitions. So maybe you can put it in the top corner.
Yeah, that's good. We have a lot of space here. Let's do it like that. So f is even So usually we say that this is the case if f of x equals f of minus x. Yeah, for all x, let's say we are on the real line.
Yeah, we are on the real line on
Yeah.
your example there,
Yeah.
so that's okay.
Yeah, so this is a symmetry property that tells us that we have some axial symmetry with respect to the y-axis. Yeah, so it does not matter whether we are left or right from the y-axis, our function is even. And well, the example that I always have in mind is, well, just our square function.
The parabola.
The parabola. Yeah, not sure if I...
That's really nice. That's good.
It's not perfectly even, but you should see that, well...
That's a symmetry property.
If we're here on x or on minus x, the value that we have here on the y-axis is the same. So this is an even function. So
yeah, this is x squared. Maybe you can put it to the graph.
Yeah.
And yeah, perfect. And now odd function.
So now odd is another symmetry property that now in terms of an axial symmetry, we have a point symmetry. So here we say that f of x equals minus f of minus x for all x in R. And once again, the example comes here that I always have in mind comes from the monomials, which are easy functions to draw, hopefully. As a function that looks like that. And so we have...
Almost, yeah. This is your x cubed.
Yeah, let's say it's x cubed.
Maybe put it a little bit to the side.
Yes. Yeah, we can move everything a little bit to the left. Yeah. I left some space here for a reason, but I think we have enough space. Okay. So what we see here again is two types of mirrorings that we do. Yeah? So we have a minus here and we have a minus also here. So we have a point symmetry for odd functions and an axial symmetry for even functions.
Maybe you can, for x cubed, you can show it for -1, for example, what happens.
Yeah, okay.
So we put in -1.
So let's say,
You're on the graph.
just calculate it here, or?
On the graph is enough, I guess.
Okay.
So there would be -1.
So we are here -1, and then -1 to the 3 is -1 again, right?
Yes.
So, but if I now multiply -1 with the minus, what I would get is a 1. And it's the same if I start with a 1 here. 1 to the 3 is 1 again.
So you have 1 on the left.
Yeah.
And -1 times -1 on the right.
Yeah. So, and we have symmetry with respect to this point here, right? So if I draw a line like that.
What is that? Is it the linear function? The diagonal?
Yeah, that should be the diagonal. Yeah. And then so we, in the end, what we just need to do, if we would to do it geometrically, we would take this point, take the distance to the origin, and then use it again here.
Okay, so that's all. There's some question in the chat. Can the derivative of a general function, say monomial again, that's not odd or even, but the derivative is odd or even?
Yeah, so this is definitely possible. So you can always try to build up examples like this. So I think what you see methods here in both examples was that we have a monomial and not a polynomial. So something that introduces some kind of an offset. Yeah, and so maybe to quickly address the example, or more of a counter example, that this does not always hold is. So let's use a function like 1 plus x squared. No, this is indeed an...
Yeah, x cubed.
Let's do x cubed. Yeah. So this would be this function, but it has been shifted.
Yes, that's also in
the
the chat.
Yeah.
Let's just say if you add something to an odd function, it's not odd anymore.
Yeah.
But the derivative will not care about the constant. Yeah.
Yeah.
So maybe you can write it down. Yeah. The derivative there is
3x to the 2.
Which is even again.
Even.
Because it's just the scaled parabola from before.
Yes. But this one here has, well, no symmetry in terms of even or odd.
Yeah, very nice. Yeah, that answers the question from the chat. We only show the one implication here in the problem 2.
Yeah. So, and what I want to use here in this problem is, again, the chain rule.
Oh.
In fact. Because if you take a close look at what happens here, is that on the right-hand side, we always have some sort of a concatenation of functions. And let me introduce
in the definition, you have concatenation, composition with just the minus sign there.
Yes. So I want to introduce another auxiliary function here.
You can give it an, maybe any color is good.
So let's call this function sigma. And sigma is a function that goes from R to R and does nothing else than mapping x to minus x. So now we can, with this function sigma...
So something happened to your... nice. Minus... Yeah, this is a really simple function.
Yeah. And now we can...
multiplies with minus 1.
Yes. So, and what we can now do is, if f is even, we can say that f of x equals f of sigma of x. Yeah, or if you want to write it as a concatenation, you can also say it's f after sigma of x. Yeah, so this is another way to, we just reformulated the definition of even in terms of this function here. So let's do the same for odd, because, well, each of our statements involves even and odd as a term. So let's do that here as well. So f is odd. So here it looks a bit different. So here we have f of x, and then we have a minus outside and inside. So we can just write it as sigma after f after sigma of x. Now, we may not need both of these formulations.
Can I say that sigma was not the best choice because the circle looks very similar.
But one of the circles.
Yeah, maybe. Yeah, do a big sigma. Yeah, then it's clear. Yes.
Yeah. All right. So let's prove the first statement.
There was the realization in the chat that the zero function is odd and even at the same time.
Yes.
Yeah. This can happen, and it's a good example for that. But the derivative has the same,
Yeah. All right.
You start with A.
Let's start with A. So f is even. That means this equation 1 here is fulfilled. Yeah? So we know that f of x is the same as f of sigma of x. So now let's show that, let's look at the derivative of f. So f prime of x is the same as the first derivative of f after sigma of x. So when we now have this concatenation here, or this composition of functions, and both of them are differentiable. We assume this for f, and also the multiplication with 1 is differentiable. So this is differentiable. And the derivative... Oh, what happened?
I think it's our music.
And So the first derivative of sigma is nothing else than -1. Right, now let's apply the chain rule here. So the chain rule tells us, well, this is the same as f prime of sigma of x. And then we multiply with sigma prime of x. All right. So now there are two different ways to write this, but maybe what we can do is we just evaluate what the sigma does here. So f prime of sigma of x, so sigma of x is just minus x. And then sigma prime of x is also just -1. So we have -1 times f prime of minus x. And on the other side, we have f prime of x. So now let's just look at these two parts here. So f prime of x at -1 times f prime of minus x. So this is just the definition that we used here for an odd function. We have a minus outside and a minus inside. So no need to rewrite it here with the sigmas, but it worked very well here for this part to know how to apply the chain rule here, or to really see how the chain rule gets applied. So genau, what we do here is f is even, and what we do here is we apply the chain rule. And then in here, this is just the definition of sigma.
And the derivative of sigma you already calculated. Yeah.
The derivative we calculated here once to have it ready.
Nice. And there we have it.
Yeah, that's a proof for part A.
Yeah, the questions are like, can you generalize that to other function spaces or to other spaces than R? Maybe that's how I interpret this question. And yeah, you can do that. You can generalize it if multiplication with -1 exists in that case. Yeah, so, but that's what you need. Otherwise, you can't compare it with even or odd.
Yeah.
Yeah, but here we deal with functions from R to R, and we keep it like that for this problem.
Yeah. All right. So that's the first part of this problem. The second part is very similar. In fact, we just do the same steps as before, but instead of an even function, we start with an odd function. So f prime of x in our case now is odd, which means we can write it as sigma after f after sigma of x. So here we used f is odd. Now we can write f, our function, as a composition. It's a composition of differentiable functions, which means we can calculate the derivative using the chain rule.
So the idea is exactly the same you use here.
It's the same idea as above. So we first do the outer derivative, so it's sigma prime of f after sigma of x times the inner derivative, which is f after sigma prime of x as a first step. So we need to do the chain rule twice if we are really precise here now. So let's maybe first evaluate this point. So the derivative of sigma is just -1, so we just write a -1 here. And so this one we already calculated before. Yeah, we did it up here. So this is nothing else than actually I can just copy what we did here before. F prime of minus x times -1. Okay, let's clean this expression up a little bit. So the -1s, they cancel out, giving us 1, and we are left with f prime of minus x. All right, let's see. We started out with f prime of x, did some calculations, And we saw that f prime of x is actually the same as f prime of minus x.
Very good.
Which is the definition of an even function. So we have also shown statement B.
Because it's hidden now, statement B was that an odd function has a derivative which is even. And exactly that's what is written there. F prime is an even function. Very good. So you showed the applications of the chain rule again. I like that.
The chain rule is everywhere, so it's good to practice it.
Definitely very important for all the calculations with derivatives. There was one comment in the chat that says you can also solve it by writing down the difference quotients instead of using the chain rule with the sigma function. And I guess, that's another possibility. Let's go back to the definition of derivative and then check what happens. And then you can see, it does not matter. If you put in minus x in the sense of the derivative, or plus x in the case of b, and then you see, this works, it's the same because of the property that the function was odd.
Yeah.
I think that works as well. A matter of taste now, which proof you find prettier. Because this one definitely does not need the definition anymore. It just uses what you already have proven with the chain rule. So quite neat. I like that. So application of the chain rule makes this a nice proof. Yeah. But just to state it, it's not needed to show the problem.
There are other ways to do it. And some may even say, well, why do you need the sigma? I just know that if I have a minus sign inside. Yeah.
Indeed. The sigma was just to help writing it down and to see how the chain rule comes in.
Yeah.
Okay, other questions? Otherwise, maybe we do a very quick last exercise and then it's good enough for today because we are already in for 1.5 hours.
All right, let's do it.
Let's change the position again. Thank you, Fabian. That was a very good exercise you brought here. I have one more, but I think we will not use... I don't want to show the whole exercise because we don't have so much time left. I'm talking about problem 4. I copied that to the empty page at the end. Also, I will upload this solution page. So you can visit my web page. It's in the description and then you can find the solution page and you can download that. If you don't find it, just write me. So now, let's move the picture again. Okay, some changes here. Nice. So, this is a differentiable function. And now we want to show something. The first part shows that if the derivative is 0 everywhere, then the function is constant. 0 everywhere means, okay, you could exclude the boundary points because they are not the problem. But essentially it means the same thing. It's 0 everywhere and then it's a constant function. So now, this is using the mean value theorem. And I already have done that in some videos, so maybe I skip that part. Apply the mean value theorem, and then you see, actually that's correct. This has to be a constant function. There's no other possibility if the derivative vanishes. And maybe also not so surprising. If you work with derivatives, you already know 0 derivative means you have a tangent which is horizontal, which also means that they are you use it for calculating maxima and minima. So, but now you have that everywhere. So you have this horizontal slope everywhere, and therefore the function has to be constant. It does not change its value. So, but the important thing is, of course, it's a differentiable function from the beginning. So the derivative exists at all points from the beginning. Okay, so let's say this one is already proven. Now I want to show how you can use that for part B, because I think this is more interesting in this problem here. Okay, problem B says we have a function that fulfills that it is its own derivative. Very nice. And maybe you already know that the exponential function does that. But now this one is a nice property. It tells you the opposite direction. It tells you if you have this property, it has to be the exponential function. There's no other choice. The only choice you have is in a constant in front of the exponential function. Is that the cat? No.
Someone started sawing.
Sometimes it's the cat.
Yeah, That's what cats do.
Yeah, and then, yeah, so I was saying, you don't have a choice. It has to be the exponential function if this nice functional equation, sometimes it's called like that, is fulfilled. It's an equation for a function. Yeah, so calculate the derivative of the function, and you see it's the same function again. Okay, so I put that to, let's see, maybe we do it like before. Put the picture in the corner again. And then we prove B. So do you have an idea, Fabian? I can tell you, we define a new function.
Yes. So you already gave us the hint that we want to use part A for this. So we need to define a new function that is, well, that has as derivative 0.
Oh, before you say that, there's a comment that I have to emphasize: the domain has to be connected. Yes. If the domain is not connected, you separate the function, and then it's a different story, because then different things could happen at different parts that are not connected. So, but that's in the function here, because it's one interval. But there you're right, yeah. If this not everything is fulfilled in this claim, it does not work like that.
Yeah.
And yeah, sometimes you have a domain that consists of 2 intervals, and you still have that the derivative vanishes. Yeah, but obviously then different things could happen at the different intervals. Yeah. So then it's not constant, but constant on the sub-intervals.
Yeah, you know? Locally constant, and then you have...
Yeah.
Yeah, you are constant on each... on each component of...
connected component.
Each connected component, yes.
Yeah, but good to point it out. If you forget about this, then you get the wrong results in the end. Because sometimes it's also just one point is excluded, and then you have 2 separate things.
Yeah.
And this happens if you work with some differential equations as well. So keep that in mind. So that's a good point. But here we have just one interval, like always. Okay, define a new function. You already had an idea.
Yes.
Of course, we use the function f.
Yeah.
And I multiply the function with something.
Yes.
And the function I multiply it with is the exponential function with minus x. So with the sigma from before in the exponent. So,
okay, yeah.
This works, and you will see that it works. But the idea would be you want to get to this constant here. Yeah. So therefore we multiply this to the left. I hope you can see that in the, we multiply this one to the left to define a new function, and this should be a constant by the claim. So this is not like it works in the end, so you say this is some magic that it works, but the idea comes immediately from the claim. Yeah, I want to get the constant out. I know I can use a, maybe, so I put this to the left. And then this is my new definition, and this is the function g. So now, to close our nice topic of today, you see what we have to use here. If we calculate the derivative, we have to use the product rule. The only rule that we didn't use explicitly yet.
Yeah.
So now let's calculate the derivative of g with the product rule. Product rule. So this one is first derivative of the first part, which is f of x, times the derivative times the function, the second function, so with no derivative involved, plus the other way around. So the first function without the derivative, but the second function with derivative, which is the inner derivative of this sigma, so of this minus 1, so it gives us minus 1. So now let's put in the colors as before, and then you already see what we can do, and maybe you immediately see it. We use our input, our assumption, our functional equation for the function f, which says this one is the same as f of x for all points x. So this is actually the same for all x in the inner interval. The boundary don't matter here, so the boundary points don't matter. So it makes it easier, but does not change the claim. So for all points in the inside of the interval, we have that, which means the derivative vanishes for all points in the inside, because now we have the same. This one and this one is the same with except the one minus sign. So they cancel each other, and we have the whole thing, and it's 0. So the g is a function defined on the compact interval a to b, where the derivative inside the interval is 0 at all points, which means by point a, you don't see that, which means here by our a, which we can show by the mean value theorem, the function g is a constant function. So this is our last conclusion of today. This is by a constant. G is a constant function. Okay, constant function means we could write the constant as a lowercase c in R. This is what we do now. And this means, putting that to the other side again, our g, or our f, is given with this g function. Yeah, let's use the definition for g, put this to the other side, and then we see it's actually what we wanted. It's the constant c times e to the power x. Yeah, knowing that this is the inverse of e to the power minus x, yeah, which you should know for the exponential function. Yeah, that's the resolution. That's the end. So the claim here is clear. This works in both directions. If you know the exponential function, you know its own derivative. And now we have shown the opposite. If we know it's its own derivative for any f, we also know it's the exponential function. But because the question was in before, this only works if you have a connected interval. And because then you can make the claim in A, otherwise not. So this is important. Everything is connected, and then it has to be the normal exponential function. Okay, so that's the proof of that. I think that's a good end for this session, because now we had everything. We started with the quotient rule, the sum rule, and the chain rule. Now we also put some product rule into it, and now you have seen some calculations, some proofs, some estimates with a Taylor polynomial. So we did a lot. I think it's good. If you don't have any questions anymore, we would call it a day and hope that we see you next time again. So if you like that, please put that into the comments, because then we know that we can do it again. Yeah. Otherwise, we would not do that. Yeah. If you don't like that, so we just do that for you, yeah, for the public. Okay. Any other questions? Maybe we'll wait a little bit if something comes in. Otherwise, something you want to say, Fabian, before we end?
It was a nice session. I liked it.
Yeah.
The choice of topics, very broad, but still around the topic of differentiability. You see, it's a very rich topic that spans even to what we saw here in the end, ordinary differential equations, which you also have a course on, right?
Yes.
Yeah.
We have started a course about that. It's not finished yet, but there are some stuff about that is already in the course. And there's a question about the multi-variable setting. I also have a course about that, so maybe you can check that out. There you need to change a little bit in the claims here. But essentially, it's the A looks similar. Yeah, if you are connected and the derivative is 0 everywhere, this is what comes out. It's a constant function. Yeah, but with the exponential claim, you have to be a little bit careful what you define there. And yeah, I also like that the topics, the exercises we chose fit together, because we put them together from different sides. I put some stuff in, Fabian put some stuff in, but it fitted. I'm quite surprised how well that works. Thanks again. Next session, do we have a next session? No, we don't have an appointment yet. We will see. Put it in the comments if you like it, and then we discuss it when we will do the next one. Okay. I don't see any other questions, so thanks again.